Hey, what's up guys? Mr. Goltz here, chemistry class. Today we are, actually the last few days we've been talking about what chemistry is, a little history of chemistry, and then also the areas of chemistry. One of the things I like about chemistry is that it is really all-encompassing. Everything is made of chemicals, all right? Some type of chemicals or molecule or atomic structure. I mean, everything that we see, touch, observe, study, everything is made of some type of chemistry, all right? And the areas of chemistry are very broad, okay? There's a bunch of them. And so today I kind of want to go more into that. For example, you got physical chemistry, you got organic chemistry, inorganic chemistry, analytical chemistry, and biochemistry. There's also a few others. All right, so today what I'd like you guys to do is to watch this video illustration. Okay, sometimes reading textbooks can seem very bland. I get that. Hearing from a teacher also not as exciting. All right, but I'm going to go ahead and segue into a video that kind of explains the areas of chemistry, talks about it a little bit more in depth, give you some visuals. Okay, and then after that I want you to answer the Google form that goes along with it so I can assess your understanding. In weeks to come, we'll be looking at ways to incorporate some hands-on lab experiences, even if at home. Okay, that means that you're probably going to end up having to use Flipgrid, which I kind of enjoy. I like seeing some of the creative ways students use Flipgrid. All right, so be thinking about possible lab experiments that you guys can do at home and demo for us so that we can all see it. And also, I'm again looking through all your debate topics. There is a few of them that have really stood out above the others, and again, I'll be rolling that out in the next few weeks, okay? So again, if you have any questions, let me know. Otherwise, it's good to hear from you guys when I do. I hope all is well. Take care.
So now I'm going to move on to look at the different fields in chemistry. Theoretical chemistry attempts to explain the structures of atoms and molecules and how they interact using mathematical methods. It's very closely related to theoretical physics and quantum chemistry, and often uses techniques in computational chemistry where atoms, molecules, and reactions are simulated in a computer. Now, simulating the proper quantum behavior of anything more complicated than a single hydrogen atom is very difficult / impossible for multiple bodies. So many cutting-edge techniques in computer science are used to try and simulate molecules and how they interact with each other. In fact, this is one of the most exciting applications of quantum computers because they'll be able to directly simulate chemical systems and will help with things like discovering novel materials and drugs and a whole lot more. Physical chemistry studies chemical systems in terms of their physics, so things like energy, force, time, motion, thermodynamics, quantum properties, amongst others. There are many subfields, like looking at the electronic properties in electrochemistry, which is important for developing better batteries, or materials science, which is trying to create materials with new properties like extreme strength, durability, or self-healing. This is a critical problem with building Earth-based nuclear fusion reactors which are reliant on new materials. Analytical chemistry is like detective work. You've got a sample of something and you need to work out what it's made of and the amount of the different components. Chemists have developed a huge array of techniques to probe and measure different properties of different materials. Traditional techniques involve wet chemical techniques like precipitation, which separates compounds depending on what temperature they evaporate. There's also a huge array of modern techniques like chromatography, where different compounds move at different speeds through a solution and so separate. Or the many different kinds of spectroscopy that can detect materials by shining light on them, or mass spectroscopy, where the materials are flung through electric or magnetic fields to separate them according to their masses. And finally, we get to the huge fields of inorganic, organic, and biochemistry. Organic and biochemistry look at the chemistry of living things, and inorganic chemistry looks at everything else, although there is still a large amount of crossover. Most of the inorganic compounds that are studied are man-made, and a lot of the motivation is to find chemicals with new properties that can be used in the chemical industry in the wider world. In fact, there are very few areas of human endeavour where inorganic chemistry has not been used in some way. There's medicine and agriculture, special fluids like detergents or emulsifiers, special coatings, materials, pigments or fuels for many industrial purposes. Within chemical production itself, catalysts are very important as they speed up other chemical reactions. Inorganic chemistry also bleeds into material science, making solids with novel crystal structures like high-temperature superconductors, for example. The list is endless. Now, between inorganic and organic chemistry sits organometallic chemistry. This looks at organic compounds which are bonded with a metal and are typically used in reactions in the chemical industry, often as catalysts. Organic chemistry looks at the structure and behavior of the molecules of life, which are typically built from a small set of different atoms: carbon, hydrogen, oxygen and nitrogen, plus a few others. Organic chemists also look at making new organic compounds with useful properties. Organic molecules all contain carbon, and the carbon-hydrogen bond is the most common structure in organic chemistry. There are a huge number of applications of organic chemistry in industry: fertilizers, pesticides, lubricants, polymers, and plastics. And in the consumer world, there's fragrances, flavorings and preservatives, and of course drugs in the pharmaceutical industry. And finally, out of organic chemistry comes biochemistry, which studies the chemistry of living organisms. Biochemistry studies components that can be inorganic, like water or minerals, but also looks at the biggest and most complex molecules like proteins, fats, and DNA. At the other end, this field also blends into molecular biology, which looks in the finest detail at how life arises out of the chemical processes inside cells. Within biochemistry, there are four main classes of molecules called biomolecules. Carbohydrates are used for structures and storing energy, lipids, which make up fats, proteins, which are very large molecules made from amino acids that have a huge array of different functions in the body, and nucleic acids that are used to convey genetic information. Research in biochemistry has had a huge impact on medicine, helping us understand infectious and genetic diseases, improving organ and tissue transplantations, working out what's wrong with you with clinical diagnostics, and of course understanding nutrition, looking at the functions of vitamins and minerals in our body. Biochemistry has also been very important for agriculture, studying soils, fertilizers, and pest controls, and there's many other applications too. So that is my attempt to summarize all of chemistry in about 12 minutes. No simple task, as it's so incredibly complicated. It has always amazed me that something so complex as a human is built on a foundation of a huge number of simple chemical reactions. Your consciousness right now is a function of the chemistry going on in your brain cells, oxygen being passed from your blood and sugars being metabolized inside them. Chemistry spans a huge mountain of complexity from a single atom to the cells that keep you alive, and I find it endlessly fascinating.